All right, it looks like we're live. Welcome to the first ever SnarkyJS week. For anybody who may not yet know, SnarkyJS is a TypeScript framework used to write smart contracts for the Mina protocol. Because these apps are based on zero-knowledge proofs, we call them ZK apps, and they have some unique characteristics that we'll get into today. With Berkeley Testnet coming up later this summer, which will be focused on ZK apps, we wanted to put together a week focused on learning about ZK apps, and in particular SnarkyJS, to help developers get going writing your own ZK apps. So today we're kicking off with a ZK apps intro workshop. Tomorrow we'll have an advanced workshop, and Thursday we'll have a gather town, a chance for you to meet other ZK app devs in the Mina community, previous builders in our first ZK app builders program, and OWYN Labs engineers working on ZK apps. Directly after both today's workshop and again after tomorrow's workshop, we will also have a 1-hour Zoom office hours that are open for you to ask any questions that you're encountering with workshop materials or anything ZK app related. We'll also have a Q&A at the end of both workshops, but the office hours are a great place for more in-depth help. Today, we're going to kick off talking about Mina and the ZK apps architecture. I'll be presenting this section. My name is Jason Borseth. I'm a product manager at OWYN Labs for ZK apps. And then I'll pass to Brandon Case, an architect engineer at OWYN Labs, who will tell you more about SnarkyJS and walk you through a Hello World example. If you've been following Mina ZK apps closely and watched our previous workshops, today may feel fairly similar with a few additional things that are new in SnarkyJS, but definitely join us again for our advanced workshop tomorrow, which is all new. And then lastly, today, we'll wrap up by giving some links to where you can find more info and have an open Q&A with Brandon, myself, and engineers working on ZK apps. So let's talk about architecture. Mina is a layer 1 blockchain. The mainnet was launched in March 2021. Whereas other blockchains are large and increasing in size as new blocks are mined. For instance, Bitcoin is 412 gigabytes as of today, and Ethereum is 755 gigabytes. Mina remains a fixed 22 kilobytes in size. And all you need is this one zero-knowledge proof to verify the consensus state for the entire history of the chain. And that, of course, is a really unique aspect because architecturally it allows for better decentralization and will remove the need to trust services in certain ways, such as SPV nodes that exist in Bitcoin. And this is accomplished, well, we call this a sync blockchain, and this is accomplished using recursive zero-knowledge proofs, in this case, ZK snarks. The cryptography team at OWYN Labs created a ZK snark that we call Kimchi, which is setupless, efficient, and extensible, and it's based on Planck 15. But the entire ZK space is really experiencing a renaissance of sorts with lots of research around performance for ZKPs. And we really expect both Kimchi and ZKPs generally to become even more powerful and performant in coming months and years. And Kimchi will both adapt and improve as well. And so this key characteristic of Mina being based off zero-knowledge proofs, in particular recursive zero-knowledge proofs, really allows us to envision a new way to design a smart contracting platform. So to give a point of comparison, let's look at Ethereum. On Ethereum, smart contracts execute on-chain, and users send a transaction specifying one of its methods with data arguments. Every node across the entire Ethereum network executes these same instructions, which is, of course, very inefficient. But Mina ZK apps use a different model. We have off-chain execution, and users can invoke one or more methods of their smart contract locally and privately on their computer in a web browser, and they generate a zero-knowledge proof from this. They then send a transaction containing this zero-knowledge proof and a description of associated state updates for that ZK app account to the chain, to the Mina blockchain. The Mina network then verifies that this proof is correct for that ZK app account, and if it is, then the state is allowed to be updated. And if it's not, the transaction is rejected. So in this case, there's no need to execute the full program over and over like is necessary in Ethereum. We just need to check that proof on chain, which is fast and efficient. So this gives us a few advantages. We achieve that succinctness of that 22 kilobyte consensus proof to verify the consensus state of the blockchain. We also gain privacy because user inputs never have to leave the browser. And users can also attest to facts about their data rather than data itself. And we'll give an example on the next slide. And then we also gain the ability to have unlimited off-chain execution. And the advantage of this too is that whereas other blockchains have a gas fee-based model, where transactions cost more as they need more compute, Mina zkApps don't require that, and they can have a flat and a more predictable fee structure. So one example of using private data locally and then attesting to it would be to prove that you have a certain amount of money in a bank account. Or maybe your credit score is above a certain amount, or your age is over a certain amount, something like this. The zkApp can run locally in your web browser, and then using the upcoming ZK Oracle, we can fetch data from different Web2 API data sources or websites, such as a bank API, and we could generate a zero-knowledge proof that says that, yes, in fact, I do have a bank account balance over that specified amount, but I don't have to reveal how much that is. And that zero-knowledge proof also doesn't contain personal information about me either. But then we can send this to the Mina blockchain in a transaction, and we can even bridge this fact over to other blockchains like Ethereum using the ZK bridge. So in that way, Mina can act as a layer to create attestations that could be used across various different blockchains in the Web3 space. To help communicate, it's useful to have some common terminology. And so for zkApps, we like to call it a zkApp for the entire thing. So the smart contract is the part that's written with SnarkyJS, which we'll talk more about later today. And the UI could be written in anything. It could be React, it could be Svelte, it could be Vue, whatever you prefer. And then with that entire thing that runs in the user's web browser, we like to refer to as the zkApp. So how does this work? Let's say you write your smart contract in SnarkyJS, and then you compile it, you build this. You end up with a couple different things. A prover function that runs locally and generates that zero-knowledge proof. And that's what runs in the user's web browser as part of their zkApp. They do some kind of operation in your zkApp, and they run that prover function to generate that proof. And so that's the one artifact that's created. And the other one is the verification key. To deploy the zkApp, that verification key that we just created is put into a transaction and sent to the Mina network. When you send a transaction with a verification key to a Mina account, we then call that a zkApp account. And it's just a Mina account in exactly the same way, except it now has a verification key, which means that it will only accept transactions that pass that verification key. In other words, they're running the expected computation. So this slide just shows that if the user sends a transaction that passes that verification key, then we know that they have in fact ran that expected computation, and we will allow the state to update on that zkApp account. And of course, if not, the transaction will be rejected. The zkApp methods, when you're writing your smart contracts, can have a couple different inputs and a couple different outputs. You will have method arguments that are the private data that a user could input into your smart contract, for instance. And you can also have on-chain values that are related to either the protocol states or the account states. And then as the output to that method, we get a list of state updates to perform, and also a list of preconditions related to the on-chain states. And preconditions are interesting because they are what allows a developer to specify that you only want your zkApp transaction to be accepted by the network if certain things are true. So maybe I want the block height to be above a certain number. In other words, I want my transaction to be only accepted at a certain point in the future. We can do that using a precondition, and that's built into the transaction. And of course, as you probably already know, SnarkyJS is written in TypeScript, which gives us all the benefit of tools that you're probably familiar with. NPM, Prettier, ESLint, you can use VS Code, and you get IntelliSense and completion for you automatically. And one other really important tool that we need to mention for writing main ZK apps is the ZK app CLI. And you can install this using npm install zkapp-cli. Be sure to install it globally. And then you can create a new project just running zkapp project and then give it a name. This is a great way to get started if you want to follow along and code anything that you're seeing in today and tomorrow's workshop. And then I want to pass to you Brandon Case to tell you a bit more about SnarkyJS.
Hello. Cool. Looks like I have control of the presentation. All right. Hey, I hope my network speed is fast enough to stream myself, but someone just, I guess Regina, just pop in there, or Jason, and tell me if I need to repeat anything. So yeah, let's dive into it. As Jason said, SnarkyJS, it's a tool that we use to build ZK apps. You use TypeScript. This is nice. Runs in the browser, runs in Node.js. It's just TypeScript. It's not a custom something new that you have to learn. You can use your existing tools, as Jason said, and VS Code and everything. I want to stress this because if you've used other CK tools, like almost all of them have a custom programming language, and that's something new that you have to learn that has associated tooling that's new. And we really strongly feel that we want to use like existing tools that are already really robust. So that's why we're using TypeScript. So when you're building in SnarkyJS, the base unit of data is a field element. You can think of a field element like uint 256 in Solidity, if you're familiar with that. It's slightly smaller, but I'm going to just hand wave over the details there. And the way that you use this is with this field type in SnarkyJS. Like when you're programming, you can use everything that you're comfortable with in TypeScript. So normal functions, normal data, JavaScript objects, TypeScript classes. SnarkyJS comes with a couple built-ins, field, bool, uint64, standard things. There's a few crypto things. If you look at that first code sample here, this is an example function, takes a field element, returns a field element. What are we doing? We're adding 1, and then we're multiplying by 2. And that second snippet there, I just want to highlight because we're using TypeScript, and TypeScript numbers are not field elements, we have to sometimes wrap the numbers in field elements. So if you want to be like very, what's the term? Like very clear, but more verbose, you can wrap every integer literal or numeric literal in like new field. But you can see in the example above, we have this nice syntactic sugar to make some APIs easier to use as well, where you can just pass numbers and they'll automatically be promoted to field elements. Cool. So let's do a bigger example. And this is, let's say, a hello world example. So what are we going to do? We're going to write a smart contract, and it has a single state variable x. And there's going to be a single method on the smart contract called update. And an update will let us replace x with its square. But it will only let us do this if we control a secret admin private key. This is a contrived example, but it's here to illustrate a couple interesting tools in SnarkyJS. So cool, let's like walk through this. X starts at 3. We can call update with 9 and a secret key. And then we get a new state where x is 9. We can call update again with 81 because that's the square of 9. And now the new state is 81. If we if we do one update, we get to 9, and we try and pass something that's not 81, then this will fail. The transaction won't be accepted to the network. The proof, the proof's impossible to create. So if you try and pass any arbitrary data, then you'll get your transaction will fail. So which is what we want. We want this smart contract to only accept updates of squaring. So let's see. To make a smart contract, you extend the smart contract class. We're going to call this hello world. And the first thing we're going to do is we're going to declare our state. So here we're saying that X is a field element, and this @state decorator tells the SnarkyJS runtime that we want this to be stored in the CKApps account state. Okay, then we're going to say what we want to do when the contract is deployed. Okay, so I'll explain all the lines here. Bear with me. So you override deploy, and the first line there is just something that you have to do in object-oriented programming. So you call super. Then we're going to set X to 3. That's this.x.set 3. And then finally, we're going to store the public key of the admin account on chain. And we could store this in the state of the account, but just to illustrate like one other feature of ZK Apps, we can store this public key in the delegate field of the account that this contract is stored in, because we're not going to be using it anyway. So that line of code will accomplish this. And I just want to point out, like, when we say this.x.set with 3, we're not actually setting the state immediately, right? Because these execute off chain, remember. So what we're doing is that set instruction is being passed along with other metadata to be applied when this CCAP is deployed in this case. We're going to see it again with update. Okay, so update. So this is a method. It has an @method decorator. And smart contracts can have multiple methods. In this case, we're only going to show one. So, and each method can do different things. So the methods of the smart contract are the actual pieces of logic that users interact with when they're playing with a DApp. So in this case, we are using public and private state. So just as a reminder, the state of a ZK app is public, so that state field, unless you're storing something that is like a hash, a commitment to some piece of data. So if you kind of hide the data before you store it. In contrast, arguments to the methods are private, unless you use some of that data to like store publicly. So which we're going to in this case. So in this specific example, we're just going to see the first few lines first. Update is first getting the value of X from the chain. And then now we have whatever X was. On the next line, we're squaring it. And then we're asserting that X squared is equal to this variable called squared that's passed in as an argument. So squared was private when it was passed in as an argument. But now on that third line, we're going to set X to the new squared value. So that makes it public. And here again, like set is not asynchronous, or rather like it's not slow, I guess, because we're not actually setting the state. In the same way that we're gonna when you say this.x.get, the actual fetching of that state happens sort of out of band of execution of the smart contract. This is why we don't need a wait. That's why I'm illustrating this. Okay. So then the next things we do. So we have another argument, admin, which is a private key. And we call admin.toPublicKey, and this promotes the private key to a public key. It's a very simple operation. And then we're going to assert that the account delegate field is equal to the admin public key. So there's this concept we call preconditions. You can assert things on the account of this specific ZK app. You can assert things on other accounts. You can assert things about the blockchain state itself, like the block height, the current time, things like this. In this case, the admin private key remains private because we're not storing the private key anywhere. We're just using it. Cool. So when we actually execute this method, when we run update with 9 and the correct secret key, we create a proof that says the following. The code within the update method was executed, and it was executed with some private arguments. And the result was an update of setting x to be 9 under the preconditions that x started at 3 and the admin public key is associated with the secret key in the cryptographic operations of promoting private keys to public keys, and that the delegate within this account is equal to that admin public key. So that proof, along with the specific updates, gets sent within the transaction to the network, and then the network accepts it if the proof is valid and applies those updates. So just in summary, smart contract, it's a class. You extend smart contract. You have state at the top. Then you have your deploy that you override. And then you add methods with this app method decorator for all of the entry points of your smart contract. And the arguments of the method are private by default. And when you execute it, you create a proof that updates have run under some preconditions, and you also send those updates. Okay, so now tomorrow we have a more advanced example. And we're going to show recursion, and it'll be a lot longer of a presentation, but it'll be very interesting if you're into advanced stuff. This is what we have for you today in the presentation. If you want to learn more, you can look at all these links, and I'm sure Jason will pop in and say something more coherent to conclude here. But yeah, we'll be around to answer questions. I mean, I'm sure we have a bunch of questions now. And yeah, that's that. Jason, you want to turn the video
on? No, that's great. The only thing to add that we need to update in our code examples is remember to export your class as well.
Yes, sorry.
But yeah, that was a great example. Yeah, this went very quickly, but hopefully this is a great intro for anybody. And tomorrow's will be really interesting. A couple of our engineers are going to be demonstrating a game and showing how you can make a game extremely efficient. So instead of having one transaction per move, you can do multiple different moves off chain using Mina's recursion, and only need to settle to the chain with one transaction. So it's going to be fun tomorrow. Definitely come back for that. And we will be in office hours as well, coming up here in half an hour, if anybody wants to hop in and meet us and talk about CCAPs.
Should we take a few questions here before we jump into the office hours?
Yeah, absolutely. Let's do that. And we can also, if any other engineers are in the audience and want to come to stage, we can bring you up as well if you'd like to help answer some questions. When will the incentivized testnet be ready? Question everybody wants to know. So timelines, we are from O1 Labs, of course, working on ZK apps. But timelines all come from Mina Foundation. So we just have to say soon, and then they will announce that stuff more publicly in the near future, I would imagine, as well. So we'll get more specifics in the near future.
I'm gonna pick from the box because a lot of them are answered asynchronously. How is contract data stored if the chain itself is only 22 kilobytes? So I can take this one. So if you go to minaprotocol.com and you scroll, it's within the first half of the page somewhere, there's something like Mina's 22 kilobytes. Then there's a link next to it to a blog post that describes exactly precisely what we mean by how we define blockchain, how we define the measurements, and everything. So I recommend that whoever asked this read that, but I'll briefly summarize. We call a blockchain the proof that says that there is a blockchain and that asserts that the current state is valid. And it's asserting that commitments to the Merkle trees of the ledgers, that, forgive my technical jargon, but sorry, I'll say this better. It proves that a fingerprint of all that data is valid. Now, certain nodes in the network store more of that fingerprint. The 22 kilobytes is enough data to store an account that you care about watching, and enough metadata about the blockchain to have full security and full assurances that what you're seeing is real in as a member of this decentralized network. I don't know if that was helpful. So specifically as it relates to on-chain state, that is a field in the account. So that's included in the 22 kilobytes of the one account that you're tracking. If you're looking at more accounts, then the amount of state that you care about watching increases linearly with the amount of accounts that you want to watch.
Yeah.
Hopefully
or to explain it in another way, just in case it helps some other people too, is I like to think of it as when we care about a blockchain, we care about consensus. So we care about what is the state of the truth for the entire history of the network. And in Mina, because they can represent that using recursive zero-knowledge proofs, it can represent that source of truth, that consensus of the latest states in that 22 kilobyte proof. So that's really what's meant by that. Whereas in other blockchains, you have to literally look through the entire history, calculate through the entire history in order to know and be assured of what the latest state is. And then you might be wondering, where is that other data? There are different types of nodes in the network as well. And there is one type called an archive node, which stores, for instance, historic transactions. But you don't need those to prove the consensus state of the network. You don't need those to understand what it currently is. But that can be useful to services like block explorers that want to be able to pull that data and show historic data. So yeah, nuances to this.
There's a quick follow-up to that question, which is, where does the data come from that we're fetching about the current state? And the answer is through a GraphQL endpoint. So nodes on Mina expose a GraphQL server, and there's some services that host public endpoints for those that aren't running their own node.
I can take one question, which was, did you write your own Lexo parser compiler for Snarky, or instrumented V8, duct tape, SpiderMonkey to get the circuits? The answer is no, although that would have been fun probably. No, it's much more mundane than that. It's just we have certain operations like add, and those operations create a constraint, like in some data structure that we have, and then later those are passed into our crypto library, and it creates proofs from them. So it's just a library. It's no compilation or anything.
I see one on here asking about ERC20 tokens. So ERC20 tokens, of course, being Ethereum's fungible token standard, Mina will have support in this upcoming Berkeley testnet for tokens at the protocol level, at the layer 1 level. So we won't actually need an ERC20 type standard to create tokens in the Zcap level, because we'll already have those at a lower level. Yeah, so I think that's kind of the answer there. It will be built in. We don't yet have support for that in SnarkyJS, but that's something that will be coming soon as well.
Oh, I think Jack, do you want to say something? I don't hear.
Oh, I'm sorry. Hey, can you guys hear me now? All right, cool. Sorry about that. We'll do. Sorry, now I lost it. It's probably at the top. Is there a local development chain available similar to Ganache CLI for the UI part? Are there web wallets available? So you actually don't need something like Ganache in order to develop with SnarkyJS. You actually can just import something called Mina from the SnarkyJS library and use that. So it makes testing actually much simpler than having to spin up like a local instance with Ethereum. And then for the UI part, there is a web wallet available called Oro that I think Jason probably knows more about how close that is to ready to go. Ooh. Is Jason frozen?
It seems so.
All right. Well, I guess we'll get another question then.
I can take one.
Yeah, go ahead.
How usable is Snarky outside of Mina? Can it output general kimchi proofs that may be verified with external tools? So I think it's the goal for us to also be able to create proofs that define circuits and so on that are usable independently. There is some. I mean that work has started, and you can. You can actually create proofs and verify them with SnarkyJS that don't have anything to do with Mina. But it's not been the main focus so far. So we could do a bit of a better job to make it everything serializable, so that you can store it somewhere. Like you can store a verification key and then take it and verify proof and so on. But that all of that will be possible, and in part is already possible. Scary. That was scary.
It was pretty intense.
Okay, having some computer issues.
Maybe you should mute yourself, Jason. All right, I will take one. One question is, what kind of storage solutions are you considering for a layer 2 on Mina? I'll just sort of answer that more generally. So this is independent of a layer 2's existence, but that is an interesting topic to explore as well. So like storage, information storage is interesting because Mina has a succinct blockchain, right? So there's three main ways to store information. So the most simple way is using the on-chain state that I showed. So that's very limited in size, of course. So sometimes you might want to store like a hash, a fingerprint, to like a much larger piece of data in that state. There's another way. So that's the first way, and that works right now. It's fully implemented. The next way that you could consider storing things is through events. So for those that are familiar with programming Solidity on the EVM, you can send events and you can put information in them and later retrieve them. This is achieved through the archive node on Mina. So it's on the chain if the chain existed, or rather the chain did exist at one point, just some people aren't storing it. But it's committed to on chain, like the exact data, not just a fingerprint of it. And then that's not fully implemented in SnarkyJS yet. And then kind of the final way is storing the data somewhere else outside of the chain. And this could be in its like fully final form on something like Celestia or Arweave or something like that. It can also be IPFS. It can also be a file on your computer that you send around to your friends. And all of these like can work, and they have different trade-offs. And all of them are not yet implemented, but we've been thinking about. So hopefully that's helpful.
So there's a cool question on here. I don't know if maybe you guys got to it while I was rebooting, but there's a question about SnarkyJS. Will it work off of Mina, off chain? That is actually something that's on the roadmap. So we want to spend some time ensuring that that's possible. And kind of the larger vision for that is interesting because the idea is, we spent all this time making SnarkyJS easy to use and continue to spend time on that. And then the crypto team has built this great proof system. And the vision is, what if we enable other people, picture like web browsers or other whatever off-chain uses, to come up with some kind of ZK related use case, and they can leverage our tools. So they don't have to build that from scratch, and they can focus on the value add of ZK. And then a great benefit they get is they get a compatible proof system. So if they want a highly efficient blockchain to interact with, they can interact with Mina for any blockchain use cases that they extend to in the future. So yeah, that's on the roadmap.
Jack, I saw there was a question about data availability layers.
Yeah, I just answered. So what I mean by that is that Mina and SnarkyJS are actually a great fit for people who want to build data availability layers, because I don't know if anybody knows how Filecoin works, but basically a big part of what Filecoin is struggling with right now, and then I should say they do actually have a solution to it. But what they were struggling with up until very recently is that even though they use zero knowledge proofs to prove that the data is available to the blockchain in a way that's relatively efficient, they still can't get it as efficient as they need it to be. And so something that's really cool with Mina is that you could take these data availability proofs. You could take these data availability proofs and you could actually put multiple of them inside of another single proof. And so this means that like you could you could make a smart contract on Mina that would incentivize people to store stuff and then allow them to prove that they were storing it routinely. So you could do something like, in the simplest case, make a smart contract that somebody could put, I don't know, let's like 100 Mina in, and then they could say, release, one of these Mina every week that somebody is able to prove that they are storing and making available a random subset of the data. And so then, the people are incentivized to store that data for 100 weeks.
Yeah. So the vision, longer term, right? We want to enable developers and Zcaps to build all kinds of things, as soon as possible. So we will also be working on, a very short-term off-chain storage solution as well, just to, enable people to do more creative stuff immediately, and then also, of course, have a much larger vision for a more decentralized and robust solution for off-chain storage down the road as well.
I'm going to take this one on, is there a light client available? So this is an interesting multi-layered question. I guess one perspective is there are no light clients, because a light client is defined as a client that's sacrifices security for lightness, I guess. And Mina has lightness on all nodes and never has to sacrifice security. So we don't like to use the term light node because it implies that there's some security trade-off. I will say there is, so ChainSafe, the ChainSafe team is building a browser node for Mina, where, just as another illustration of how light it is to run Mina without sacrificing security, we will have or at some point soon. I'm not going to promise any dates, but there will be a browser node, and as that sort of integrates with ZK apps, this is really cool because, like, dApps on other chains, most users interact with them through publicly hosted nodes, and in that sense, like, are you really even decentralized? So the cool thing when the browser nodes are shipped, you'll actually be connecting to the chain in a decentralized manner when you're interacting with a ZK app. So that's just super interesting. So yes.
Can I take real world use cases? Awesome. So there's a lot of things that you can do that are really unique with Mina. Obviously, you can build a game like Dark Forest. I think that's actually a place where there's a lot of space to do something really cool. It's possible to build these limited information games, and if you can build limited information games and put them on the blockchain, then people can prove that they're smart in a way that might, like, help them get a job or something. And so I don't know, you could have like some sort of computer generated puzzle that got harder every time somebody solved it, and then at some point, the person who solved it would, everybody would know, like, okay, nobody's solved it in 3 months, so the person who just solved it is really smart. So that's cool. But you can also do things like anonymous DAO voting. You can build some applications so that they run almost entirely off chain and are still secured. And so obviously Mina smart contract code in general executes off chain, but it's possible to, for example, what we'll be going over in the advanced workshop tomorrow is an example of a game that two players can play against each other and verify that, one player can verify that the other player is playing according to the rules, basically. And so all of this happens off chain. You don't pay any, transaction fees to do this. And then once the game is over, at the end, you submit sort of a proof of the entire game to the Mina blockchain, and just pay the gas for that one transaction. And then if one of these players decides to stop cooperating at some point, you could implement a system where the player who made the last move and had the highest number of moves in their proof could submit that to chain after like 4 hours and get a prize or something like that. So those are two pretty cool use cases. There's also lots of stuff with like attestation and creating credentials that are privacy preserving. And of course you can build like almost anything you could build on Ethereum on Mina.
There's also a question about NFTs. I don't think that's been answered before. So NFTs, we actually had a group at ETH Amsterdam start to hack on creating NFTs for Mina. I think NFTs, the way that we've talked about them, they will belong best within the ZK app layer as opposed to the protocol layer, because we don't actually want to bloat our account ledger for every single NFT. So it makes more sense to implement those inside of the ZK app. We don't yet have a standard around that, but I imagine this would be an amazing project for somebody to tackle, for instance, in the ZK app builders program, or just on their own if they're interested. But yeah, so that's going to be best implemented at the ZK app level. But it's not implemented yet.
Yeah, maybe this is also one good example for another question, which is how do we get to contribute to Mina ecosystem? So I think a great way to contribute is start building on SnarkyJS. So there's lots of stuff to do, and there's kind of a gap between like us, we build the primitives, and users, and in between we will need lots of libraries and apps that do basic stuff that we have on other blockchains. I think there's a huge room of opportunity there. So if you want to contribute, I encourage you to find an application and try to build it.
Yeah, I love that. I think there's more to add to that. It's a pretty big question. We will also have the upcoming Berkeley testnet with a bunch of challenges around ZK apps and interacting with ZK apps or writing your own and sending them, this type of thing, and you can earn different points. But that would be extremely useful because we really want to battle test the network in different ways. So just having more minds doing different things in different ways allows the network to be tested much more realistically. So that is a huge way that people could contribute. And then just using the tools, right? So downloading the CLI, creating a project, and then writing something with SnarkyJS, and then giving us your feedback too. Like in particular, if you find anything that you're like, hey, I think actually maybe we could create a slightly cleaner API, or we could create the function signature to do this in a slightly different way, and it could be more intuitive to people. We would love that kind of feedback too, because one thing we're really passionate about is trying to make ZK apps the best developer experience possible. And we really think the feedback that we've gotten is that that seems to be the case in the ZK app space so far. I hope that's what everyone else experiences, but we definitely want to keep at it and adding more features and keep continually adding those features while keeping it easy to use, as easy as possible. So just any feedback and jumping into the ZK app developers channel to let us know would be amazing. Yeah.
I will grab this one. There's a question about transaction speed, how it compares with Solana. So Solana is like, Solana's purpose is like fast Ethereum, and same with like most of the projects these days. Mina's purpose is not fast Ethereum. So we haven't spent too much engineering effort on like optimizing performance yet. So like the transaction speed is not too fast on Mina right now. There's no theoretical like limits of keeping it as slow as it is. It's just like engineering effort. Right now we're focused on like enabling these new types of applications through ZK apps. And yeah, like there are, you'll want to use a trick like you'll see tomorrow. If you need to do something with a high number of transactions, you spin up your own CK rollup to do what you need, and then you settle on chain just whenever you're ready. So
yeah, and obviously the more naive solutions that massively bloat the blockchain are a convenience near path. But exploring these things like Brandon's talking about, like rollups, is likely a better long-term vision, and it's a really natural fit for zk apps and Mina, since the recursion is is built into the layer one. So that's probably a more ideal scaling path. But like Brandon said, there's a lot more opportunity for performance improvements at the base layer too.
I also want to answer the top voted one. How can contracts interact with each other on chain? In a more traditional blockchain, you'd have callbacks between contracts. How would this work in Snarky? So Martin already gave an answer, but I can say more. So in SnarkyJS, so everything is off chain. That means if you call another contract, you download the source code for both of them. So, or maybe both of them are on a website. And you create one big proof that you called this method with these inputs, and the method called the other method with that inputs, and returned that. So basically, one smart contract calling another just becomes one big transaction with multiple proofs for each of the smart contracts that were involved. So it's a bit weird, a bit unusual, but it works.
Yeah, and I think the important thing here is that it's possible to do this. This is something when the team was designing CK apps, we wanted to make sure that every kind of interaction that people are familiar with on the EVM, there was some way to achieve something of equivalent expressiveness with SnarkyJS and CK apps.
Oh, there's an interesting question here about. Imagine there will be a lot of smart. My question just moved. Where did it go? Something about smart contract standards in the future and how to propose those, and would MIPs, mean improvement proposals, be the best way? Yeah, I think so. Mina Foundation has kicked off the MIP process, and that seems to be the best route for major proposals to to discuss those as well. Smaller things also, a great way to discuss those is to open an issue and create what we would call an RFC, but it's just kind of your proposal of what you think this might look like. And of course, SnarkyJS is open source too, so you can submit pull requests, and that's always welcome. But if it's something big, it's definitely worth opening an issue to start a discussion first, or not big, but if it's might be worth discussing it first beforehand. But yeah.
Yeah, I think we'll transition to the office hours soon, where you can just come in and talk to us on camera. I think make sure that you click on all those links, metaphorically, that are shown here. Show up tomorrow. Be a wonderful, powerful force in the universe, creating CK apps, SnarkyJS, or something. I don't know. Yeah, and thank you for being here.
Yeah, thanks for joining us.